Hi everyone, my name is Ugur. Today I will talk about our D3N project, which is a multi-level cache for object stores, which is designed to improve the performance of big data analytical workloads. I'm from Boston University, and you can see the list of collaborators of this project here. Here we see a private data center with a hierarchical network topology and data analytical clusters. Many modern data centers create data lakes as a separate clusters. Data lakes typically implemented as object stores, which usually implement S3 interface such as our own Rails gateway on Ceph. Object stores are immutable, which means objects can never be modified or rewritten again. The whole point of a data lake is that every cluster in the data center can access it, and cluster shares the data store in the data lake. Recent literatures talk about full bisection bandwidth networks for cloud data centers. However, in practice, only few hyperscale data centers have full bisection bandwidth. The rest of us have heavily oversubscribed networks. For example, in our own data center at Mass Open Cloud, new clusters are added all the time, and the data center network becomes imbalanced even more. Therefore, bandwidth to the data lake is limited. If all compute clusters access data lake over the network to read and write their datasets, it results in substantial traffic over networks that may be heavily contented. Due to the network limitations, big data workloads suffer from poor performance. But the good news is these workloads have a tremendous amount of reuse within the cluster and between the clusters. We highlight the characteristics of 4 different production traces which are publicly available. For instance, 2 sigma financial hedge fund trace shows that different jobs analyze the same datasets, and their data analytical people run their analytics on these datasets over and over again. Big data applications should take advantage of caching to speed up their runtime. There have been many efforts to cache the data in the compute clusters, including Alexio, which is the most well-known solution today. These solutions are designed to be cached for a single cluster. Unfortunately, with these per cluster caches, if multiple clusters access the same datasets, they all pay the cost of fetching the data from the data lake and independently caching it, wasting a huge amount of network bandwidth and cache space. We designed D3N, a data center-wide shared cache, and the design of D3N is motivated by 3 important properties we observe in our data center. Our data center is an academic data center with a shared data lake with over 70 petabyte of data. 70 petabyte of storage. We find first thing we observe is sharing. We find sharing datasets between different clusters quite common in our environment. For instance, a single user may use multiple frameworks. There are popular datasets which are accessed by independent cluster. Also, in an academical environment, researchers often collaborate with each other. Means they access the same datasets from their own institutional clusters. Second thing is the locality. The bandwidth internal to the racks and between the racks of the same institution is usually much larger than the bandwidth between different clusters and to the shared data lake. It is important to satisfy most requests local to where the requests originate. And the third thing is the statelessness. Compute resources are elastically shifting between clusters growing up or shrinking down to match the demand. Avoiding state on compute resources is a general concern. We believe these requirements are not unique to our own data center, and actually many data centers out there have the same requirements. These observations have led to several important design decisions that differ us from previous caching systems. We created a cache which is an extension to the data lake and shared across all clusters in the data center. For instance, if data is produced in one cluster, we want to be able to see it immediately in another cluster and access it from the cache without needing to go back to the data lake. Second, we integrated read-only SSD cache into the RGW. And finally, to enable upstream of our design, we implemented simple and purely local policy for cache management. As a result, we have a multi-level cache with consistent hashing at each level. Now let's look at the high-level overview of our architecture. We have a data center with a data lake, a hierarchical network topology with oversubscription. First, we strategically place cache servers on each rack. the first layer called layer 1 or L1, and L1 cache acts as a proxy for the data lake, storing data locally for reuse. Clients' requests are always forwarded to the local layer 1 cache. Layer 1 reduces the traffic going out of the top of rack switch. If there is a reuse within the clusters, then we group cache services in pools and create layers. Here, servers in blue cooperating in pools create a distributed cache layer called layer 2, which reduces the traffic going out of the cluster switches. Cache misses on layer 1 are redirected to the upper layers, and we are using consistent hashing. If we have more reuse between clusters, then we can create upper layers in a similar way. As you can see in the figure, we collocate different layers on the same cache server. We run a lot of evaluation, but I just want to briefly talk about this one where we're trying to show the impact of D3N on realistic workloads. We run the publicly available Facebook trace, which has a 75% reuse, and we set up the D3N with using 2 cache servers. Each cache server has 1.5 terabyte of NVMe SSD, and we had 2 networks set up. One of them we have FastNIC, which has 2 40 gigabit network connectivity to the data lake, and in the second experiment we tuned the network and create a slow NIC, which each cache server has 6 gigabit network connectivity, and we also have a Ceph cluster which runs across 90 spin disks. So here in this figure, you see the trace completion time with 2-level D3N and with vanilla RGW, which doesn't have a caching mechanism. The x-axis is the bandwidth to the Ceph cluster that we use in our experiment. In this graph, lower is better. As you see, even with very fast network setup, the caching can improve the performance by 25%. For more slow network setup, runtime of workloads improve by 2.4 times for the full workload and 3 times after the warm-up phase. As can be seen here, cache is highly effective, greatly increased storage system throughput, and thus application performance. Another benefit of D3N is the reduction in the inter-cluster traffic. In this graph, we see cumulative data transferred from the backend storage for the slow network experiments. With D3N, only 5 terabyte of data is transferred from backend after warm-up. D3N do not saturate the network links. On the other hand, with vanilla RGW, the Ceph link is nearly always saturated, and it transferred 23 terabyte of data. As seen in the figure, D3N reduces the backend traffic more than 4 times. You can find more details about our project by visiting our web pages. Also, we have a published paper for D3N, so you can read that paper to learn more about and see our interesting results. Currently, the D3N code is productizing, Red Hat is productizing D3N code. So the Red Hat RGW team working on the upstream. And that's all. Thank you very much for listening me. I hope you enjoyed the talk.